Last time we were talking about the concept of regular languages, which were the class of languages that a DFA can accept. So instead of just thinking, here is a language, how could you construct such a state machine that accepts that language? Now we're thinking about what are the class of languages that any DFA could be constructed for? What is the power of the ability to represent with states and transitions within this concept of a total function where every state, every vertex has an outgoing edge for each of the characters in the alphabet? So we talked about that, talked about the concept of a family, and then we named that family of languages the regular languages. Then we also talked about the fact that there was a limitation to DFAs, this concept of, well, they don't really store data. They don't store state aside from the state that you're in. There's no storage, there's no memory associated with that. So that ends up being a big limitation for it, but it's a nice definition for a family of languages that don't rely on storage. They just rely on which state you are in and not on any history of what you've visited. So, question for you then. How can we prove that a language is regular? I ask you, here is this language. Is it regular? What could you do to prove that? DFA. Draw a DFA for it. It's that simple. It's basically proof by example. Here is a DFA that represents it. Of course, just because you've drawn a DFA doesn't mean that it's correct. You would need to go and show that your DFA is correct. And there's not necessarily an easy way to do that without a very intuitive argument or a bunch of unit tests, but even unit tests don't prove that something is true. They just give evidence. So this is how we're going to be doing this, so it's worth getting some practice. Speaking of practice, more practice. All right, here we have a language that is going to be the character A followed by the string W followed by the character A, and W can be anything in the star closure of AB. So these are all strings that start and end with an A and consist of only A's and B's. Let's go ahead and draw a DFA for that, and as always, feel free to work in groups. Did I tell you she's a Stop skipping, Josh.
Skip one day.
Mine too.
What does it take? You want to
Yeah.
The string is just a.
I agree, first one was gone, and also statement this morning is, it's the weekend already, right? Yeah. My poor wife is working provision this week, there's really to get a weekend. But I can't come say it's great. No, at least you get a weekend.
No.
Should be this one, but yeah, let's use it.
Yeah.
Because look at the.
We will be more than it is not.
What does the star closure mean here again?
It means zero or more of either or. So we can have, it's basically any number of any selection. So the empty string is in the star closure. A is in the star closure. B is in the star closure. AA is in the star closure. AB is in the star closure. BA is in the star. BB. AAA. Literally zero or more of any selection of those. Think of it as any string, basically. W can be anything that consists of A's and B's.
Oh, yeah, I did too. I did like 8 points.
Can't do it, all the wrong. What's that?
We'll wait for the exam.
Exam?
Wait till it matters, then the answer. will-
Yeah. And then don't share my.
Or if it's just.
Oh, I understood it. Like,
So I was already.
It's accepted.
Yeah. Okay.
we didn't.
Yeah. You have to. So. You'll chain that is to your file. Zero files. Two.
I can make like little.
So you just have another one that's.
By the temporary copy. Okay. I also have, I have a copy in my office, I can look. Okay. I only have one, so whoever comes to me first. It says, yes.
The extent of the fall, you see from the start, you want to put yourself in the
But it only goes back to this one.
I'm getting excited today. I just saw it.
Yeah. See, like, and on.
Let's start with B.
Hate these photos.
Starts.
The only issue would be that I cannot have textbooks that cost much in my classes. I feel so bad. So I could have required the textbook in this class, but it's expensive, so no.
No, because it has to be. So.
Yeah, I'm okay with the book that's between $20 and $45. Or $3 for the Kindle version, yes, but.
Because that saves no matter.
Beyond that, no, not here. Maybe if I were teaching against that. If I were teaching against that guy, I'd probably find the most expensive textbook I possibly. I'd be one of those professors who publishes my own book and then makes it $7,000 to buy it for my class. I couldn't get away with that.
So we don't.
So it already has.
I'm my own publisher, it's literally stapled together.
Just like a day, he was super.
All right, how we doing? We ready to go over it? Anyone want some more time to work? All right, let's discuss. As per usual, we're going to start with some state that is an initial state. What's the easy condition here? The first character we see, we can immediately reject anything from here. The first character is what?
B.
A B. Then there's no way for it to represent or to be in the language of AWA. So let's go make a trap state. And definition of a trap state on every character in the alphabet is just going to self-edge, go to itself. Great. We start with a B. There's no way to be in this language. Pun intended. All right. For A, we see the first character that we want. That has nothing to do with either of these states. If we were to loop on Q0, if we saw AB, we could end up in the trap. And that could possibly now create something in AWA. So we do not want to reuse this state. We need some new state to represent that. So we will make a new state. All right, we have finished Q0 and Q trap. From Q1, we now need to start being able to handle this W and or this last A. Where do we want to start? A or B? What makes the most sense?
A.
Start with the A. If we see an A, is it an A that's in W or is it an A that is the last A? Does it matter?
Well, we lose on B.
Yeah, we can loop on Q1 on a B. So this becomes the second A that we have seen, regardless of where it is in the string. So yeah, let's start there. We can say on a B, make a self-edge to Q1. It says no matter how many B's we see, it's not the A that we need to see in order to know that this string ends with that A. So we know that at least the first time we exit Q1 is the second A that we see in the string. We'll go to a Q2, I'll make this a final state, because if we see AA, that is a W of lambda. There's nothing in it, which should be accepted. By the star closure, there could be 0 or more characters in W. If there are 0, AA means that it's in the language. So if we end in that accepting state, what happens if we see a B? Do we stay in that accepting state?
No.
Where do we go? Which of these existing states, if we see a B once we've seen our second A?
One.
Back to Q1, that says that we've still seen that first A. And we need to see another A in order to get back to Q2. What happens if we see an A from Q2? Stay in Q2. Doesn't matter how many A's our string ends with. All but the last one are going to be part of W, and the last one is going to be that last A. Note how there's ambiguity as we're reading this string from left to right. When we see the second or later A, we don't know if it's the last A or if it's something before the last A. But this structure, by building the structure in such a way, it does not matter. Wherever the string ends, it ends. And we have now perfectly decided whether the strings are in the language or not, based on that. So to give you an example of that, we could do something like just ABAA. From Q0, we read the A, go to Q1, read the B, stay in Q1, read the A, go to Q2, and now if the string ended there, this A that we just read would be the last A, the one that we terminated on and accepted. But if there's another A, or if from here there's a BA, then we can either stay in Q2 or go back to Q1 and back to Q2, and only the last A that we read is the one that puts us into Q2 such that we accept. Every other one put us there temporarily before we took another edge of some kind. Questions on this? Hopefully this is reasonably similar to what you came up with. Anything I can explain further? Teleports. Should not be allowed. There's another one up there, it's blind. No questions? Okay. We starting to feel a bit better about these?
Yeah.
There's something that should be similar to what I did. Last one. We're going to go back to the last question. But now we want to show that that language concatenated with itself is regular. So first, if we had to define L squared, as in write out that language. So L is that AWA, such that W is in AB star. If we had to do something similar to this, what would L squared be? This is just saying LL, basically. There's a first half and a second half. The first half comes from L, and the second half also comes from L.
AWA.
Close, very close, but not quite. What is the issue with that? There's a very small issue. So W is a squiggle. It's more notational than anything. Yes. Why is that an issue? It's forcing it to be the same W.
Yeah.
That's the issue. By using W as a symbol, there is, within this meaning, W stands for something. And there could be separate parts of this that are different W's from the first half and the second half. So we need subscripts under those W's that show that they can be different. What is the middle of this does not have to be the middle of this. So now we would say such that W1 and W2 are both members of AB star. All right, now go ahead and see if you can find a DFA for this language. Have it? Okay. You know, from being there, I was trying to do, I don't know. Step down here. You told it out here.
Listen, I'm cheating on my ears. Oh, you know, you can't say it on there. Oh, cheating, that's also. Especially how we get money. You have like change 280 back to that. Yeah, well, yeah. I would go small. But sneak. One of the races. You don't even have security. Because so this then we can understand this on 31st. And let's see, we'll see it and we cross the notice set. So right, we go to A, go to S, and then there, that's our new one.
And then you can go to the skin, once we do it, we can do like that. Yeah. So if you get beaten after you get your first day, you can get beaten by. So if you get beaten, get beaten. And if we go deep, basically. It would. That's something that's been increased. Let's do it goes A, D. So A, B. Of 8,000 times. Because basically, when I'm in now let's use A. Let's go to A and you could probably. B. If you use it in 2 ways, then you need 2 notes going forward. And we ain't like well, now you have no say. You can stay.
This example is empty. I can't remember.
Because I got the data stream.
Just.
No, things were not done.
So both of these have no here, so A, nothing, A, nothing, A. Now you accept that, A. Which is now the appointments.
But once you get
You know, transition with that.
That.
you are going to just.
You have to say something.
Now it's from,
That's just the beginning.
for the last, for the. Yeah, it's not.
It's a good start.
Yeah, so guess what? There are some other counter examples.
So if I get all the way to the final state, that means that I have something that is already in the form. Bring one AW2A, so that happens if I add a BA. I had to see that should also be accepted, so we go to the draft state of B. Maybe it's final state, I just gave away of escape that, so it'll pay going to draft state is right.
So we're asking all this. Yeah. Correct.
You should.
Where would it come to?
And you just.
Yeah.
You don't know if it's ended yet. The track is only through like 100% sure that after this change.
This creates an interesting dilemma that I don't know if some people have run across yet. If you had a string something like this, how many different ways are there to construct AW1A, AW2A out of this string? Quite a few, right? You could have A blank A, so that's W1, and then A, so this is your W1, and this is all your W2. You could have a W1 that is these and a W2 that is that, with a single middle character in each. How do you embed possibilities into your DFA, or do you need to? The answer is actually that you don't need to. The DFA that you construct will interpret this ambiguity in one way or another. Just because there is one such way to break this down, we don't need to find all such ways to break this down. We just need to know that there is such a way. So because of this, think of this character as the second A. And that will always work. How are we going? Who wants some more time to work? I think we have answers. Seems like no one wants more time. In that case, we can go over an answer. So we can start almost like we did before. We can kind of have copied over most of the last answer. Nothing really changes with regards to the first part of this, except for changing what used to be the final state on this last A can't be final anymore because we haven't read the entirety of a string in this new language. So we'll start with a Q0. We'll go to a trap state on a B. On an A, we transition to Q1. This is going to be the first A, so we can loop here on a B, just like we did before. And when we see our second A, we're going to move to Q2. This is what used to be our final state. So now we have everything up to Q2. It was before that when we saw a B from Q2, we went back to Q1. Do we still want to do that? If this is that second A, this A, what comes after that actually needs to be another A.
Yeah.
So if we see a B from here, that actually does not adhere to that AA form. And we do need to go back because we need to see those back-to-back A's in order to proceed. So for that reason, we do still go back on a B. When we do see an A from here, we know in order to get here now, the only edge into Q2 was reading an A. So we had to have seen that AA combination in order to escape Q2 on reading an A. So we can move onwards. This is going to represent the first A of AW2A. So we need the ability to read W2. So this is going to look fairly similar to something that's copy and pasted from the first half of this. This is the equivalent of Q1 in this sense. We're waiting for the second A in AW2A. So we can self loop on a B. When we see that second A, we can reach a final state. From here, it's just like the old final state from the first part of the problem. We see more A's, we continue to accept. If we see a B, we just need to go back here because we need to see another A to be back in the acceptance. Probably worth running through this with a couple of examples. Who has an example string they would like me to run through? It doesn't have to be accepted necessarily, just any string as complicated as you want that you would like to see run through this to see why it would or wouldn't be correct.
Maybe A.
Let's say that again.
A, B,
A, B.
A, E,
Okay, so we have W1 and W2. There's only one way to interpret it. Starting in Q0. Move to Q1 on the A, stay in Q1 on the B, move to Q2 on the A, move to Q3 on the first A from W2, stay in Q3, move to Q4 on the last A, accepts. And since there is a way to break that down into W1, W2, we should have accepted it. Any other example? Anything you can come up with, either that you think might be rejected that should be accepted, or accepted that should be rejected? Is there anything that looks wrong to you about this or something complicated you want to make sure works? Yeah.
Back to A2 from A3 and have Q3 as the final state instead
So go back here on an A,
on a B.
on a B. So if we do this on a B, and then self-edge this on an A.
Yes.
What happens if we go Q2 on a B, then we're back in Q1, and we need to see 2 more A's in a row? I think that becomes, see if I can come up with what would work. We take A, B, B, A. And I'm gonna mark this as a potential final state. If we make this, then this is our W1 and this is our W2, so this should be accepted in this case. So from Q0, we would go A, B, B, A, and end up in a non-final state. That would be extremely close. There aren't too many counters to that.
Yeah, I was looking at your solution, I was like, I know it's wrong, but I can't explain why.
Yeah, that's tough. That's a really close solution. It can be reasonably apparent that your solution is correct, and it takes a lot. It takes a very edge case. It'll work for 98% of cases, 99% of cases, where there's that one counter that makes it not quite right. And that's a big challenge on homeworks in this class, is going through the work to make sure that your solution is correct. Because it'll be very easy to make a small mistake and very easy to make a large mistake. And if you're doing this at the last minute, then you don't necessarily have the time to go through your work and make sure that you find that your answer is fully correct. But that is an excellent thing to note and a great example of something that is very close. I feel like that adds a lot to be able to see just how small changes make it difficult to find a counter for it, but it does exist. Questions on this? Everyone have everything they need from the board? Feeling like we're ready to solve some DFAs on a homework? There are office hours if you get stuck. That said, there are some challenging ones, especially with the grammars on this first homework. Okay. Here's a solution on the page. I think that's what I drew. Pretty sure that's what I drew. I don't necessarily refer to these before I go over. No, not the one I just opened. All right, we're about to start a very fun discussion. So I need to introduce a concept to you that is a theoretical concept, but it's a very important concept in computer science theory. And that is the concept of non-determinism, because it finds a way to show up. And if you understand it, it actually makes determinism make more sense. So the concept of non-determinism. Let's start with determinism. Everything that you have ever written, every DFA we've drawn so far in class is deterministic. What that means is, within the scope of DFAs, every step is uniquely determined by the current state. You can imagine exactly the same thing. If you write a program and you're in the middle of a debugger and you say, step over or step into, there is always one place you will end up. There is no ambiguity as to what your program is going to do. Given an input, you can know, given the program, exactly what the next statement is, the next statement is, the next statement is, all the way until completion. That is determinism in a nutshell. So Every program you've ever written is deterministic. Every DFA is deterministic. Because given that you're in a state, you're reading a character, there is one and only one transition you can take to get to the next state. Further examples. Write a program that guarantees you'll crack a password, you know it's exactly 6 characters through brute force. You get unlimited attempts, you don't ever get locked out. So, how many attempts will it take? Let's say that these passwords can be made up of uppercase letters, lowercase letters, and digits, and that's it, no symbols. Some expression. Upper bound on the number of attempts it will take. If it's the last one you check.
Isn't it like the factorial of? So it was uppercase and lowercase letters
And digits.
and digits of that.
Yeah.
Of the,
So there are 26 uppercase, 26 lowercase, 10 digits, 0 to 9, 62 possibilities. Can passwords repeat characters?
Yeah.
Yes. So a factorial would be useful if we could not repeat characters, because then a character that had been chosen for the first character, the first character in your password could not be chosen again. So that's how you'd have the total -1, the total -2, the total -3, because you couldn't repeat characters. If you can repeat characters, then it's just exponentiation. So there are 62 possibilities. There are 6 possible characters, 62 to the 6th possibilities. If you were writing a deterministic program, you would need to check 62 to the 6th possible strings. That's quite a few strings, but the modern computer could do that basically instantly. The concept of non-determinism, on the other hand, gives us a possible sequence of next steps given the current state. So we need some way of designing a program such that instead of searching, there are a couple ways to think about this. You can either guess and know that your guess is correct. Whatever it is that you guess, it's correct. Or you can imagine that someone has told you what their password is. How long does it take you to verify what they told you is correct? I say my password is 123456 because I'm a very secure person. How many character entries does it take? How long does it take for you to verify that is correct? You just need to enter one thing, and then you can answer yes, what you told me is correct, or no, what you told me is not correct. And it's proportional to the length of the password. If my password is now 1 billion characters, it will take 1 billion key presses to answer yes or no. If it's 6 characters, 6 key presses to tell yes or no. So it becomes linear in the length of the password instead of the length of the password times the possible number of combinations. So rather than exploring and searching for the next successor, we're going to assume that the correct next successor is selected. It's another way to think of this in terms of a program is you've forked this program into a bunch of children based on all of the possibilities. So from the root node of this tree, we're going to have a branch of 62 branches, and on each one of those branches is a different character. We know that one of those characters must be the correct character, but we're going to take our process and fork it into 62 child processes. Each of those child processes is going to take and assume a different first character. On the second step, each one of those 62 child processes is going to fork its process into 62 child processes for determining the second character of that password. Now we have 62 times 62 child processes running at the same time. Then we're going to guess the third one. So each of those 62 times 62 child processes is going to fork into 62 child processes. How long would that process take to run, given that we have basically limitless parallelism? That's that same idea, right? It's going to take linear time with proportion to the length of the string, assuming that we could create those child processes instantly. In 6 steps, one of those many child processes, the 62 to the 6th child processes, would have cracked the password. And it would have happened in linear time. Does that make sense? So this is the concept of non-determinism. In terms of computation, you can just imagine that you have infinite parallelism. You have infinite RAM. You have the ability to just, as long as there exists a path to the solution, you will find that solution without searching. You can attach yourself to any of those ideas. Those are the ways that I have heard or thought of non-determinism myself being explained. I prefer myself kind of the child process idea because it ties to something that I've done before. It isn't a completely theoretical idea. And it's basically reality if I had an infinitely powerful computer that could just fork child processes upon child processes without limit. Eventually, you'd run out of RAM for this. But hey, if you had infinite RAM, you could write a program this way. So I'm going to introduce another state machine type that uses this idea of, well, if we could utilize infinite process forking, then we could use that power to represent a state machine. So here is a non-deterministic finite acceptor, or a non-deterministic finite automaton. Same quintuple as the DFA, with the exception of the transition function, which now, instead of going from one character in the alphabet, going from one state to another state, now we can have more than one of those. So we're relaxing the restriction that we can only, from a particular state, have a single edge outwards on a single character. I think this will make much more sense if I translate this and tell you just the differences between a DFA and an NFA in a nice, easy 3-point list. There are only 3 differences. First, we're going to allow what we're going to call a lambda transition. This is a transition from an outgoing state to an incoming state that does not consume a character in the input. I like to think of this as teleportation. We can move from one state to another state instantly. It's also kind of like a process fork. It's an optional transition. You can either stay in the current state or teleport to the new state. So in one sense, you're in both states at the same time. Second difference. Multiple transitions out of one state to consume the same input. So before, we were in something like Q0. We had a transition on an A to Q1. We could now, in an NFA, also have a transition out of Q0 on an A to another state, Q2. This is allowed. This is saying when we read an A, fork the process, one process goes to Q1, one process goes to Q2. Last, you don't need to specify every possible transition. So this can be a partial function rather than a total function. So before we needed trap states, in NFAs, we don't actually need them because we don't have to specify every transition. NFAs are capable of concluding that if there is no transition that is defined on the current character, we immediately reject. There is no possible way to accept because the transition is not defined. Any quick questions about those 3 differences? We are out of time. So we'll come back to this on Monday and start to get some examples of NFAs and start working with them. And start asking questions, what are the theoretical differences between DFAs and NFAs? What can an NFA do that a DFA can't, and vice versa? Questions like that. See you Monday for further questioning your own existence.